Well,
would you like me to do a quick introduction?
sure.
Okay. So our next speaker is Chris Bretherton, who is a faculty member in applied mathematics and atmospheric sciences at the University of Washington, as well as being the senior director of climate modeling at Vulcan Incorporated. I won't go through Chris's list of distinguishments. They're extensive. He has received 2 major awards from the American Meteorological Society, including the Jewel G. Charney Award and the Horowitz Lecturer. And so with that said, I'll let Chris give his talk on improving forecast skill of a global weather and climate model using machine learning.
Okay, thanks, Thomas. So like Sebastian's talk before this will be a very applied talk, but the application is completely different. For the last year and a bit, I've been on leave 90% to actually work as part of a private philanthropically based effort to improve the forecast skill of global weather and climate modeling using machine learning. And I'll describe this effort a little bit more later in the talk, but it's been an interesting change of pace for me. And this effort is actually also in collaboration with a major national climate and weather forecasting laboratory called the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey, and we have a collaborator there as well. Let's see. Our motivation for this project had to do with what climate models are good at and what climate models are less good at. So even on regional scales, climate models are fairly good at predicting or projecting the temperature trends which are likely to occur as we pump more and more greenhouse gases such as carbon dioxide into the atmosphere. So this picture shows you on the left a bunch of different climate models run partly over a historical period starting in 1900 and partly out to the end of the 21st century. And each one of those is a gray line. What's shown here is their decadal average temperature prediction for Washington, Oregon, and Idaho, an average. And the solid line there is actually the historical record out to the year 2000. So you can see that all of these climate models agree with the historical record fairly well, and they all agree roughly on how much warmer it's going to get over the next decade, which is over the next century, which is alarmingly warmer in this particular scenario where we don't do a lot to mitigate greenhouse gas emissions. So there's plenty of room to act there, but for many purposes, we'd also like to know about precipitation change, in particular when we're trying to adapt to the climate change, which this temperature increase is going to cause. And here, climate models agree a lot less well. So again, the historical record show there's a lot of decade to decade variability. That's the solid line on the right. And if you look at models over the last century, you can see that they tend to track that, and they track the fact that we haven't really seen much precipitation change yet over the Pacific Northwest. But they also show that in future, some models predict a precipitation decrease over the Pacific Northwest, and other ones predict a significant increase. And those are very big differences for planning for the future, and we'd really like to have more confidence in what answer we can give to society there. So our goal then is to improve climate models to predict rainfall predictions over land. So why is this difficult? Well, global climate models have to run for hundreds of years. They discretize the surface, discretize all of the components of the climate system, including the atmosphere, ocean, land surface, sea ice, with a mesh of points, and the grid columns over which a climate model is discretized are typically 25 to 200 kilometers apart. And of course, in a place like Washington State, there's a lot of small scale terrain features, which are smaller than that. So that's one issue. But a bigger issue actually lies in the tropics. So in the tropics, a lot of precipitation occurs from thunderstorm systems, looking like the one in the lower right, which are quite complicated objects and vary a lot on scales less than 25 kilometers. So the picture on the lower right, for instance, probably shows a region that's about 25 kilometers on a side. And so what we do is that we have to represent those in the model somehow, and we use something called parametrizations. So I've developed parametrizations. In fact, I helped develop one of the parametrizations schematized in the middle right for one of our two largest national climate models. But these are not designed according to any set recipe. It's subjective how you do it. They tend to be a bit of a cartoon of reality. So different climate models use different representations. This leads to uncertainty, especially when it comes to predicting the future. In particular, they cause climate models to predict different precipitation patterns, trends, and extremes. So one way around this is to try and use a finer grid model for which these features are actually resolved on the grid. And in fact, we can already run such models. They're called global storm resolving models. They have a global grid horizontally of 1 to 3 kilometers. They pump out terabytes of data, but they do better simulate individual storm clouds and mountains. However, they're way too expensive currently to run for hundreds of years. We can run them for 1 year, perhaps, but not 100 years on a large supercomputer. So we do have such models in the United States. They're sort of development models right now. One of them was developed at the GFDL lab, which is a NOAA lab. It's called X-Shield, and it's based on our national weather forecast model, which is called FE3GFS. And this is the output from this model, a snapshot of that output showing cloud systems over the globe at 3 kilometer resolution. And if I had told you that this was a satellite image of the Earth, you would probably not have been able to say that I was wrong. It's actually sort of hyper-realistic, or at least it looks that way. It's not that it doesn't have biases, but it certainly looks like it's resolving the atmosphere quite realistically. What do these models look like? Well, FE3GFS is actually an open source global atmosphere model used by NOAA for weather forecasts. It represents the Earth, the atmosphere as a cubed sphere. It uses a staggered grid, 80 vertical levels. And the two horizontal resolutions we'll talk about here are 3 kilometers, what we just talked about, and we'll actually try to use it to improve a prototype climate model on a 200 kilometer resolution. So about 64-fold coarser. Operationally, for our global weather forecasts in the US, we use a 13 kilometer version of this model. And the finest resolution we could really use for climate is about 25 kilometers. It has a bunch of representations of different physical processes, such as the land surface and exchange between the atmosphere and land and ocean surfaces, radiation, processes such as small scale waves, which can break in the atmosphere and impart drag, turbulence in the atmospheric boundary layer, cloud processes, both on the grid scale and smaller than the grid scale, and cumulus convection. And it uses a different set of such representations than most other climate models. Why would we want to use a 3 kilometer model? Well, we expect a model like that should be able to do a better job with representing precipitation processes, but of course the proof is in the pudding. This is some evidence to that effect. These are 40-day averages, the longest run we've done with this 3 kilometer model so far. What is shown is the bias compared to the 40-day mean of the our best observational guess at rainfall around the globe during that period of simulation. And what you can see is that the 3-kilometer model has some biases. Blue or low precipitation compared to observations, red or high precipitation compared to observations. But if you compare the 200-kilometer version of the same model, you'll see the biases are in many places much larger. For instance, over sub-Saharan Africa and over the Himalayas in India, where we're having the Southeast Asian monsoon at the time of year simulated. So here you can see the fine resolution model certainly seems to have the potential to inform the coarse resolution model. Okay, so now this brings me to what my group at Vulcan Climate Modeling, VCM, is doing. So this is a philanthropic open source project funded by Vulcan Incorporated in Seattle. This was Paul Allen's holding company while he's alive. Now it's under the directorship of his sister, Jody Allen. And our group, which was sort of specifically asked for by Paul Allen before he died, involves 2 interlocking groups working to improve weather and climate forecast models. So one of our groups, which is led by my co-director, Ollie Führer, is using something called a domain-specific language, which will allow the model to run faster on modern heterogeneous high-performance computing with a variety of accelerators. So this will enable these very high-resolution simulations to be carried out for longer. My part involves using machine learning trained on these very high resolution simulations to try to increase the accuracy of rainfall predictions by a more affordable climate model. Target 25-kilometer grid, what we've been doing so far, 200-kilometer grid. These projects interlock with each other in the sense that Ollie's project would help produce larger training data sets for my project, and some of what we do could feed back into making a better model for his project. So far, we're 1 year into this pilot, and our focus has totally been on the atmosphere as opposed to other parts of the climate model so far. We do have a group of about 15 people at Vulcan working on this, and purple indicates all the people who came at some point from the University of Washington, which is about half of our group. Of those people, myself and Noah Brunowitz, who had a data science fellowship, have some affiliation with applied math. Noah had me as his primary advisor while he was a data science fellow, but Nathan Kutz was his secondary advisor. Okay, so weather and climate models are really the same thing, because climate is the long-term statistics of weather, and as a result, we have designed climate models basically as weather simulators, which are carefully coupled to land and ocean, et cetera. Climate models, on the other hand, have to simulate tens to thousands of years, and so they have to use a coarser grid than your typical weather forecast model, which only has to simulate 10 to 14 days. However, there's an advantage to trying to make your climate model into a good weather prediction model, which is that weather variability is an observable test bed for improving some of the processes very important to climate, such as clouds and rain, which basically track with storm systems that are part of the weather. Now, the way that we conceive of the problem, and in fact, most climate and weather models conceive of this problem, is that we separate our problem into 2 parts. So one of them is the airflow on the resolved scale. And here, bar indicates a variable averaged across a grid box. So bar indicates the resolved scale variable. So V is the velocity. And so you can see that we have equations for temperature-like variable, S, humidity, Q, and horizontal wind components, U, on the coarse grid. So they have advective contributions, Coriolis, and pressure gradient for the velocities, and then they have these terms which are associated with the physical parametrizations and unresolved processes. So Q1, the apparent heating, is due to latent heating, radiation, turbulent transports unresolved by the grid, et cetera. Q2 is the apparent moistening. That's again due to the condensation and rain out of water vapor, for instance. And there's an apparent momentum source due to drag, which we haven't really considered very much in this work so far. And the critical assumption that we make in our work is that all of the effort we're going to use, for which we're going to put into machine learning, goes into column physics. So the idea here is that the physical parameterizations in one particular grid column of the model depend only on the local atmospheric column conditions. So for instance, we might input profiles of humidity, temperature, and winds, as well as sunlight, surface properties, and so on, and then get outputs which are tendencies of those same quantities, humidity, temperature, and winds, from those physical processes. And this simplification is quite justifiable under the conditions which we typically run our climate models. Well, so our goal in Vulcan climate modeling is to use machine learning to improve the parameterized physics. So how do we actually do this? So we want to basically train a machine learning correction to supplement some or all of the physical parameterizations of a coarse grid climate model, so it evolves more like a reference model, which we think to be more accurate. And the main reference model type we're interested in is a fine grid global storm resolving model, which may have biases, so it's not a perfect representation of the atmosphere, and which we can only run for short periods of time. And we do have the benefit of some previous work, especially work that Noah and I did while at the University of Washington, that suggests that this can work in some idealized settings, such as an ocean-covered planet. We have another possible reference, which is that we actually currently, as part of our weather forecasting enterprise, make grid observational estimates of the atmospheric state called reanalyses. So we can use these directly. We can only use them for the historical period in which we've observed weather well from satellites, so the last 40 years. And they may be of lesser quality in places where there aren't enough observations. But at this point, they're pretty high quality as well. So we'll use both of those as bases for machine learning. Okay, so what we use that is something called a tendency difference method. So we imagine we have some advected scalar, A, which is a function of time, t, x and y, horizontal coordinates, and eta, which is a terrain following vertical coordinate. And we know A from the reference model as well as a function of time and position. And we imagine that we have a pre-model, a pre-coarse resolution model before the addition of machine learning, which consists of resolved scale advection plus some set of physical parameterized processes that we take from our normal parameterizations. That subset could be none of those processes. It could be all of those processes. It could be something in between. Then we define the tendency difference, which is the difference between the rate of change of the reference tendency and that from this pre-model in the same grid box. And this is what we try and machine learn in each grid column as a function of the atmospheric column state. And if we could machine learn it perfectly, then the resulting machine learning corrected coarse grid model would approximately match the reference model. Of course, we can't learn it perfectly, so it remains to be seen how well this can work. Now, one way this is really different than normal machine learning is that we are not doing pure machine learning, we're doing hybrid machine learning, where the machine learning is interactively coupled to other model components. So the normal offline skill of a traditional machine learning exercise is that we have input data, we use it to train the machine learning, we reserve some of the data for validation, and we see how we do. And from that validation data, we can figure out already how our machine learning is working. And we do that too, but then the real test of our work is we put it into this hybrid system. We interact it with the flow solver, and then we run our model in a weather prediction mode, and we see what happens and how well it's able to follow the reference state. So it's more complicated, and more things can go wrong. And in particular, even if we have offline skill, a variety of things can and do go wrong here. So the first and most basic one is our simulations can become unstable when we couple the machine learning with the rest of the model, in particular the flow solver. Can blow up within as little as a day or so. Even if we have stable simulations, the model might not make accurate forecasts. And even if it makes stable, accurate forecasts, it may still drift when run for longer and produce biased climate. So these are actually very hard tasks to make work in this context. Okay, well, before we started trying this at Vulcan, Noah and I had done some of this work before using something called an aquaplanet model of an ocean-covered Earth, in our case, a tropical belt running from 45 south to 45 north with a sea surface temperature that varied only with latitudes, warmest at the equator and coldest at the edges of the domain, the north and south edge here. So the north edge is the top, the south edge is the bottom, and east and west are left and right sides. And what you see here in A is sort of what the model at its original 4-kilometer resolution, how it simulated the cloud field at one time. So what we do then to use this for machine learning is we imagine we have a coarse model that we're going to try and do this machine learning correction for, which is 160 kilometer by 160 kilometer horizontal resolution, same vertical resolution. And the pre-model is dynamics only. So we're going to machine learn all of the rest of the parametrizations. And to do that, what we do is we take each 160 by 160 kilometer region of the fine grid model, we block average horizontally. We use that to generate 160 kilometer by 160 kilometer coarse grain of that fine model. And we calculate the difference of the tendencies over 3-hour blocks between that fine model and the coarse dynamics only model that we have already. And then we learn this as using a neural net as a function of the column conditions. And we found in doing this that this is actually quite hard, but after a lot of work, we were able to make this model stable. And we were able to make 5-day forecasts of something we care about. In this case, the field that you're seeing is a 5-day forecast on the right of the field on the left, which is the column integral of the amount of water in the atmosphere, which is very related to where it's going to rain. And the little features here are basically fronts in mid-latitudes where moist air is being transported poleward, and then a band of very moist air over the warmest sea surface temperatures where a lot of rainfall forms. Unfortunately, the simulation drifted very rapidly and was sort of unusable after 10 or 20 days. But be that as it may, the opportunity came up to try and do something based on this at Vulcan. And so here our goal then is to do the same thing, improve the parameterization of clouds and precipitation and weather and climate prediction skill. But rather than working on an aquaplanet, we are going to try and use a full complexity atmospheric model and machine learn an improvement to that. So no model problems here. We're going to go for the real McCoy, which increases our potential impact, but confronts us with a lot of practical challenges. And one of them is actually just even working with the model. So you know, the version of the model that we have access to is run at GFDL, or run actually at Oak Ridge, but behind a firewall, which we in Seattle cannot get to. Furthermore, the code that Noah uses is closed source, so we had to work with an open source variant of that code. And we have no compute infrastructure at Vulcan. So basically what we had to do is we had to get a coarse resolution version of this open source version of this model to run on the cloud, which was not trivial. this model is written in Fortran, so to use it with machine learning, it proved to be convenient to wrap it in Python, which was also not trivial, and then build out an advanced machine learning workflow on Google Cloud to make all of this work and to actually do machine learning. So actually, I want to talk to you about software engineering, but software engineering is by far the largest challenge of this project. Instead, I'm going to focus more on the conceptual and math issues. And one of them has to do with the fact that the Earth has a lot of topography. So this is actually a north-south section through a region across the north side of the Himalayas. So it's at the 3-kilometer resolution, you can see the mountains in the brown underneath the atmosphere. And you may or may not be able to see the terrain following coordinates layers above that. But the idea then is that as these model layers go over the terrain, they actually undergo 5-kilometer vertical excursions in the course of the 200 kilometers across a given coarse grid cell between those two red bars. And the temperature as you go along that model layer varies wildly in such a way that just averaging along model surfaces is really not very effective. You lose a lot of information. Instead, you want to average horizontally instead of along model levels. So we had to figure that out. So how to coarse grain over topography was one problem. Another problem is the one of initialization shock. If you coarse grain your model, even doing the best job that you can, and then stick it into your coarse resolution 200-kilometer model and use it as an initial conditions and let the model go, it turns out that you generate an enormous amount of initialization noise. So for instance, what's shown here is the vertical velocity field at the start of a coarse resolution run, and then 7 and 14 minutes into it. And if you look in the little red box, what you see is sort of a lot of red and blue dots emerging everywhere where there's mountains. And so basically what's happening is everywhere where there's mountains are these initial adjustments that take hours to settle down to basically get the model compatible with the coarse grid properly and get it settled down onto some kind of a slow manifold. And so this complicates calculating the tendency difference between these models. So what we had to do instead was use a nudging strategy where instead of actually initializing the coarse model with the coarsened fine res data, we actually nudged the coarse model to the fine res model with a nudging timescale that was chosen to be sufficiently long as to keep this noise, this initialization noise, down by keeping the coarse model near its slow manifold behavior, but fast enough to keep the model state close to the coarse model. And it turns out that this procedure does work, and you can machine learn the nudging tendency as the difference between the coarse and the fine resolution model. So that's what we do. We machine learn the column vector of the nudging tendency as a function of the column state in each column of our coarse res atmospheric model with 200-kilometer resolution. Now we've actually used two kinds of machine learning. We have used random forests and neural nets. Random forests are kind of like the SUV of machine learning. They're very robust. They can go anywhere. They're not necessarily super duper accurate. Neural nets are less robust, but they're kind of like the Tesla. They can go really fast on the right road and give you really cool results. There are pros and cons to each of them. Now, it turns out that using either kind of machine learning, we can actually do a pretty decent job. So it turns out that those nudging tendencies, even if you average them globally, have they're non-zero. So they have a vertical profile, which is not zero. Here, model level of 80 refers to the surface, and model level of 0 is the top of the atmosphere. And these are profiles of the global time means of the nudging tendencies. And here, blue is the target. That's what we're trying to machine learn. And the orange and gray are the global time mean averages from the random forest and neural net. You can see they track each other almost perfectly. We can machine learn the mean really easily. It's just that we can't machine learn the variability nearly as well. If we look spatially, it's not quite so simple. You can look at just the spatial time mean as opposed to now the vertical time mean. So now we column integrate those nudging tendencies and look at them as maps. And so the target is on the left and the two machine learning strategies are on the right. Now you can see the two machine learning strategies are different. The random forest tends to smear out the target fields. The neural net sometimes tends to over amplify them. And so they do start giving somewhat different behaviors here. Now you can interpret the fields we're trying to machine learn here a little bit. So the top field is called the moistening. So it's the column moistening. And so when it's blue, it's negative. That means that there is net drying. So it means that the coarse model is not drying out the atmosphere enough in most parts of the world. And so since drying of the column corresponds to removal of water vapor, basically the way that happens is by condensing the water vapor and turning it into rain. So it says the coarse resolution model is not raining enough. And this is telling us how much it's not raining as a function of position. So these patterns that are very important then to predicting and improving the coarse model prediction of rainfall. The bottom panel, the heating, is mainly the latent heating that's associated with that rainfall. So wherever it's drying a lot, the blue in the top, there's a lot of condensation that corresponds to a lot of latent heating produced by the random forest that's heating in the bottom. So there's a strong correlation between these two fields. Okay, so where are we? So let's consider some forecasts that we can make with this. So the acid test of this kind of machine learning is to do what we call prognostic or forecast runs. Since we only have a 40-day fine resolution run to compare with, we can only do 40-day simulations because that's how we can tell if the fine resolution and coarse resolution model are tracking each other. What we find is that both forms of machine learning can increase the forecast skill of the coarse resolution model in 10-day forecasts and in mean rainfall distribution, which is great. They have some climate drifts and variability, which isn't so great. And we do still have some stability issues, which we think have to do with the formation of regions of negative moisture, which is unphysical, but the machine learning scheme can allow. Just to show you how we do this, this is shows an example of a reference. So that's on the bottom of a field called 500 millibar height, which is basically the pressure distribution in the atmosphere at a particular level. So blue is low pressure, yellow is high pressure, and the winds tend to flow along these pressure surfaces. So this level is useful because it tends to steer all the storm systems through the atmosphere. And so what you could do is look at this field and the simulation and the reference. In this case, the reference is an analysis of the observations at some distance into the forecast. And take the root mean square of the difference between these two, average it across all grid points, and then see how that increases with the forecast time. So as the forecast goes on, the forecast loses skill and ceases to match the reference. So the error goes up. What you see is the original model that we started out with, our baseline model with all of its normal physical parameterizations at 200-kilometer resolution, is in gray. And our two machine learning corrected versions of the model are in blue and orange. And they both actually reduce the error. So they basically increase the effective forecast skill by about a day. So the errors at 6 days with these machine learning schemes are the same as the forecast error at 5 days with the original model. For reference, weather forecast centers take about 10 years to get that increase in skill from their models. So this is not a small improvement. Furthermore, we're able to improve the mean error, the RMS error in precipitation averaged over the 40 days as well. Over the last, kill the first 5 days because the model is still kind of getting itself spun up over that period. But in particular, compared to this baseline model, our machine learning corrected models actually reduce the root mean squared error of precipitation by 15 to 20%, which again is actually not easy to do. However, there are still issues. So one issue is if you take a look at, say, the lowest layer temperature in the model, and you do a longer run at 160 days in this case, and you look at two different versions of the machine learning, the random forest and the neural net, and you compare those with the baseline model, which is in light gray, and the model we want to track, which is the fine resolution model in the dark gray, you can see that there's a big cooling of the model between 10 and 20 days, and then it kind of drifts around in an unphysical way with the neural net. With the random forest, it crashes after 30 days, which also isn't good. So, so those are problems. You see similar drifts in other fields, like the column amount of water integrated across the globe. So we're not perfect. And we think this is actually due to the formation of patches of negative humidity, which we've worked on. Okay, so let me just show you, in, well, one more thing. So in terms of progress toward climate change prediction, we're trying to set the same kind of game up in warm and cold climates. So we're making fine resolution climate simulations in climates with 4-degree warmer and colder sea surface temperatures everywhere over the globe. And then we'll try and train a single machine learning scheme to deal with the entire range of climate so that we can look at climate change response with it. So that's our goal. Now, I'd just like to talk about one other approach. It's not useful for climate change, but it's an interesting standard for comparison, which is to use observations as your reference. So now we're using a gridded observational analysis as our reference data set. And it turns out that we can get these analyses pretty easily. So we can make them, we can get them more easily than we can make high resolution simulations. It's easy to train now on a full year of data since we have 40 years of data. Obviously, the training is only limited to the historical period. So this is really more useful for weather forecasts and seasonal climate prediction than climate change prediction. An important thing we did at just in the last couple of days that miraculously improved the performance of these was to add a limiter which basically prevents the machine learning from creating negative humidity. And with that limiter, which we haven't yet been able to put in the other method yet, our machine learning method is actually has all the same advantages of our nudge to fine approach that we talked about before, but no drift, and it can run stably for at least a year, maybe indefinitely. So if you take a look at its forecast skill over a 10-day forecast, once again, with this, this new reference data set, observational reference data set, you can beat the forecast skill of the original model by half a day to a day. And now you can run the model out for an entire year. It still drifts in fields. So this is the total water path, the amount of humidity averaged over grid columns over the entire globe. So here, what we would like to do is shoot for the light blue curve on the right, which varies with season. The original climate model, which we started with, was the dark blue. So it's actually not unbiased itself. And our best machine learning scheme here is the green curve, which is similarly also biased, but now biased in the opposite direction. But anyhow, so at least now our biases are not much larger than other climate models that we might want to compare with. Okay, so in conclusion then, we've developed a sophisticated cloud-based workflow for applying Python-based machine learning to a full complexity operational global numerical weather forecast model that was written in Fortran. So there's a lot of software engineering there. We developed machine learning schemes that improve the skill of global weather forecasts at 200-kilometer resolution, which is about a factor of 10 lower than we actually use. So this is sort of still a demonstration test. And also the time mean rainfall distribution, which is important for climate. And our current machine learning scheme need to add some physical constraints, and that preventing negative humidity was one of them, to keep them from excessively drifting from a reference climate. We're still kind of working on making this a great climate model as well as a good weather forecast model. So that was all I had to say about the project so far. We've got another year to try and make it work even better, and hopefully then it'll be something that's actually ready to transition to real world climate models and weather forecast models. So thanks.
All right, great. Thank you, Chris, for a very
you.
interesting talk. I see we have a question from Irina